Sand falls from a conveyor belt onto a conical pile at a rate of 10 cubic feet per minute. The radius of the base is always equal to half of the pile's height. At what rate is the height of the pile increasing when the pile is 5 feet high? We know that this is going to be a related rates exercise as we are given a rate at which a unit per time measurement is happening. In this case, the sand is falling onto a conical pile at a rate of 10 cubic feet per minute. Let's draw a picture of what this may look like. Here we've got a conveyor with some sand falling onto a pile, and this pile is structured in such a way that the radius of this pile is always half of the height of this pile. So we can write it like this, that the radius is 1/2 of the height. The other equation we will need for this setup is the volume of a cone. As we know that the sand is falling onto a conical pile. And since we also know that it's happening at a rate of 10 cubic feet per minute, cubic feet tells us that this will be a volume. So the volume of a cone is 1/3 pi r squared h. What we know about this situation is that the volume of the cone is changing at a rate of 10 cubic feet per second. And since a rate depends on time, this will look like this: dV over dt, the rate at which the volume is changing with respect to time, is equal to 10 cubic feet per minute. And what we're trying to figure out is at what rate the height of the pile is increasing. So we are looking for the rate at how the height is increasing with respect to time. And we also happen to know that the height is already 5 feet. So h equals 5. And by looking at this equation for the volume of a cone, and since we are using implicit differentiation with respect to t, when we get to this r squared times h, we would have to use the product rule, and then we would have to know what r is, and then we would have to know what dr dt is, and we don't know anything about the rate at which the radius is changing. What we do know is everything in terms of h. We know the height of the pile, and we're trying to find the rate at which the height is changing. So it would be great if we could have this equation all in terms of h. And we have this equation here to help us with that. If we substitute 1/2 h in for r, our entire new equation will become entirely in terms of h. So now it looks like we can simplify this thing and take the derivative in order to find dH dt. If we square this quantity, we get 1/4 h squared. And if we simplify this even further, we can combine these three terms into pi over 12, and we can combine these h's into h cubed. From the previous slide, we have the volume equation all in terms of h. We have our given information that the height is 5, the rate at which the volume is changing with respect to time is 10, and that we need to find the rate at which the height is changing with respect to time. Now we can just take the derivative of both sides. The derivative of v by the power rule is just 1, and since we are taking the derivative with respect to t, we need to multiply the rate after that. And the derivative of h cubed by the power rule is 3h squared. And since again we are taking the derivative with respect to t, we need to have the rate multiplied immediately after. Now all we have to do is substitute in our information, that the h is 5, that the dv dt is 10, and we can solve for dh dt. So on the left side we will have 10, and on the right side we will have pi over 12 times 3 times 10 squared, 5 squared, dh dt. The left side we will leave as 10 for the time being, and the right side, when we simplify 3 times 5 squared and multiply it by pi over 12, we end up with 75 pi over 12 dh dt. And this fraction simplifies to 25 over 4 pi. And this is still equal to 10 with dh dt being multiplied. When we multiply by the reciprocal of this fraction, we will isolate dh dt. So that looks like 10 times 4 over 25 pi equals dh dt. And when you simplify this fraction, you can divide both of these numbers by 5, and then we can multiply 2 times the 4 and get 8 over 5 times the pi is 5 pi. And this is feet per minute. So our rate at which the height is changing with respect to time is 8 over 5 pi feet per minute.